Assalamu alaikum wa rahmatullahi wa barakatuh. Friends, welcome back to my channel. In this session we are discussing synchronous rectifier. When we see any power supply, switch mode power supply, it has primary section that contains PWM driver, sometimes PFC section, and these components. Then there is transformer. After transformer, most of the time we see rectifier diodes. Schottky rectifier or simple rectifier are used there. But here in this power supply, it is using a MOSFET instead of rectifier diodes. To control these MOSFETs, it is using SR controller, synchronous rectifier controller. It is also known as active rectifier. Primary, secondary. When we are using rectifier diode, it is called uncontrolled rectifier, uncontrolled rectification. How much voltage are coming in the secondary, these will be rectified and it will drop 0.7 volts in case of silicon diode, 0.2 volt or 0.3 volt in case of Schottky rectifier or fast rectifier, MBR. So this is uncontrolled. When it is using this circuit, it will not behave like this circuit. It will provide an extra layer for voltage regulation and current limiting. Primary PWM is also maintaining the voltage by means of PFC and flyback. Output of this circuit is again regulated to provide extra safety for the load, extra safety for the circuit, and extra safety for this board. Let's see this circuit. It is using TEA1761 green chip synchronous rectifier controller. Different specifications and details are written here. We will see the circuit. Pin out. Pin 1, that is SR sense, synchronous timing input. Then pin 2 is ground. Pin 3 not connected. Pin 4 is driver. Driver output for SR MOSFET, synchronous rectifier MOSFET. Pin 5 is optocoupler pin. It will drive optocoupler. Pin number 6 is voltage sense. Pin number 7 current sense. Pin 8 is VCC. Here is its block diagram. It receives supply voltage at pin number 8 and ground. Then it will receive voltage and current values from the circuit, from current sense circuit and from voltage sense circuit. There is over temperature protection in the chip. If everything is within parameter, voltage are maintained, current is in limit, and temperature is not too high, then it will drive optocoupler to control the primary side. It will sense here SR signal. When transformer will start to switch, its pulse will reach here. That time this circuit will control the gate of the MOSFET to provide output. If there are high voltage, it will reduce the pulse size to reduce the voltage. If the voltage are dropping, it will increase the pulse size to allow more voltage to proceed on the output. Here is its simple circuit. Transformer, primary side controller. Primary side controller is driving this flyback transformer. When voltage will reach here in the output, positive voltage are reaching directly to the output, and there is current limit resistor for this optocoupler, and optocoupler cathode will be driven from this IC pin number 5. Pin number 8 will receive positive voltage from the positive line. Then there is voltage divider network. It will provide voltage value, how much voltage are there at output. When this output line will receive 8.5 volt, that are startup voltage for this IC, then it will start to control the gate. Negative side low side of the transformer is reaching to MOSFET. When this MOSFET will switch, it will pass the voltage to the output side, and there is current sense resistor. Pin 2 is ground, pin 7 is I sense, current sense pin. So it will sense how much current is there in the circuit. Let's see this circuit on microscope, and we will draw this circuit here. These 2 points, 1, 2. These are output points of the transformer winding. That are these 2 points. One point is coming here at 1, 2, 3 points. These are positive terminals of output capacitor. This is transformer primary winding, and positive side is reaching here to the capacitor bank. And these positive voltage are reaching here at this jumper, and these are reaching at this point. It is inductor, output filter, this one. So positive will pass through this inductor to the load. Then from this jumper, these voltage are reaching to this rectifier. This end, it is connected to VCC capacitor, that is here, and these positive voltage are reaching to pin number 8 of this IC. Pin number 8, and there is capacitor, that is VCC capacitor. Now if we check, same positive voltage are reaching here at this point. Here is 105K resistor that is connected at this point. Then this end is connected to 12K resistor, and center node is connected to pin number 6. Positive, and this end is grounded. It is connected to pin number 6. This is voltage sense. Now the same positive voltage are reaching to this jumper, then 1K resistor, and it is going to optocoupler anode pin. One kilo ohm resistor, optocoupler, anode pin. Then cathode is connected to pin number 5 of this IC. Cathode is connected to pin number 5 of this IC. In parallel, there is 2.2K resistor, that is biasing resistor. For this optocoupler, that is this one. Then there is 10K resistor and this capacitor connected between positive line and the drive pin. These two are compensation components. Capacitor, (10K resistor). Pin number 2 is grounded. Pin number 1, this one, it is connected to this point, then this resistor, 5.1K resistor, and it is connected to transformer this point. That is second side of the winding. You can say this end, now it is coming to this MOSFET block. We will check the number of these MOSFETs. Here it is using FKP202 N-channel MOSFET. FKP202 202, N channel 200 volt 45 ampere continuous drain current. Its pin 2 is drain, pin 3 is source, and pin 1 gate. Gate is connected to 10 ohm resistor. This one 10 ohm, 10 ohm. Two MOSFETs in parallel. Why two MOSFETs? These two MOSFETs are connected to decrease RDS on. So when there is very low RDS, resistance drain to source, it will decrease the switching loss. It will not dissipate too much power. And these two resistors are connected to pin number 4. Pin number 4 is driving. Pin number 3 not connected. Pin 2 is ground. Pin number 1, which we discussed, the same voltage which are coming to MOSFET drain pin, these are reaching to this 5.1 K resistor. 5.1 K resistor. Then these voltage are reaching to pin number 1. Here is a diode. Then there is LT222. This rectifier, these will protect this IC from negative spikes, transients from this transformer switching noise. Here is RC snubber that is connected between drain to source pin for its fast recovery. Resistor, capacitor, it is connected here. When this voltage will come out after switching, then these are provided to these capacitors. These capacitors, this point. Then these voltage are reaching to this point. These 2 points. This metallic bar, it is current sense resistor. This end is grounded. Ground end, it is coming here to IC ground pin. VCC capacitor and pin number 2. How much current will flow from this shunt resistance? It will cause to drop voltage here. Same dropped voltage will be applied to this resistor, 4.3 K resistor. Then it is coming to pin number 6. This point, it is connected to ground point for this side. Then we have shunt resistance. This shunt resistance signal provided to 4.3 K resistor, and it is going to pin number 2. Then it is passing through inductor, and this is negative out or low side, positive, negative from this inductor. Between positive and negative there is decoupling capacitor. When it will receive voltage from here, these two resistors are 105K and here it is using 12K. IC is TEA1761T SR controller. Then here it is 203, this resistor, and here is LED that is at this point. Resistor, LED, and it is connected to ground. 203, 20K. So this is the circuit configuration. Let's check it practically. If you don't have good practical experience in electronics, never do this experiment, because here are live voltage. $24 volts. Always take care for the safety. Never touch the circuit in the primary side. I will connect oscilloscope probe to low side, and now I will check signal at pin number 4 of this IC. This signal without load. This drive pulse without load. When we will connect load in the output side of this charger, this adapter, the pulses will increase. When the load will decrease, the pulses will decrease. Now if I will remove load, the pulses will return back to normal, so that it will allow a limited charger to maintain the voltage at output point on these capacitors. These pulses are reaching at capacitor, positive terminal. After passing from the filter, these are regulated voltage. These are without load, which are reaching at capacitor. When we will put load, capacitor will receive these pulses. When there is load, output will be stabilized. Before filter, there are pulses. After filter, these are regulated voltage. So this is the working phenomena of this IC. When there is no load or light load, it will produce small pulses, small duration pulses to drive MOSFET. When the load is connected, it will provide more pulses to provide more voltage in the output, and it will monitor the voltage all the time. If there is overcurrent condition at that time, these are normal current pulses which are coming out to this resistor. When there is short circuit condition in the output, we can see this IC will turn off. It will turn off the MOSFET. The IC stopped to allow to pass the current. Why? Because there is short circuit condition. When this short circuit condition will be removed, it will start working at normal. Primary side will remain working, but it will control the output. If you think this video is informative, hit the like button. If you have any question, please write in the comments. Thanks for watching. Assalamu alaikum wa rahmatullahi wa barakatuh.